Hi everybody, welcome back. In this video we're going to start a several-part series talking about telescopes and their capabilities. Not just telescopes that observe in the visible part of the spectrum, though those are extremely important, but also telescopes that observe in other parts of the electromagnetic spectrum. So this material will also correspond to, for those of you who like to look at the OpenStax textbook, a 2017 edition, that is, Chapter 6 of that. And we will investigate several leading questions. One, why are we building bigger and more expensive telescopes? And how do radio and infrared and X-ray and gamma ray telescopes work? And how do astronomers communicate with interplanetary spacecraft? So here's a picture of an old observatory, an old picture of an old observatory. Now this observatory is still in operation. I have visited it many times when I was a graduate student at UVA. It houses the McCormick refractor, an extremely fine, very nice observing instrument. And at the time that it was created, for a very short period, it was like temporarily the largest refracting telescope in the world. I think for like a month or something like that. Refracting telescopes work by using lenses to focus the light. And the distance between where the lens is and where the light crosses is called the focal length. Now keep in mind that's not where the image forms, and that's something that we're going to come back to later. But there are also reflecting telescopes that do something similar, except they use mirrors to bounce the light back. There are certain advantages to refracting telescopes and certain advantages to reflecting telescopes. But refracting telescopes use lenses, reflecting telescopes use mirrors. So I mentioned that focal length that was in that last picture, but again, that's not exactly where the image forms. The distance between where the lens is and where the image forms is known as the image distance. And notice that in this diagram, the focal length is from the lens to where these rays are crossing. So the image distance is longer than that. But for reasons that will become clear soon, with refracting telescopes, you generally want a very long focal length. So the lens is going to be at the opposite end of the telescope from where the eye is, or where the eyepiece is, and then the rest of the tube is going to be the distance over which the light rays end up coming together, crossing the focal point, and then forming an image. Now, Galileo's telescope was a refracting telescope, the first telescope that we know of for sure that was used for scientific observations. There were other telescopes and spyglasses before, but they weren't, as far as we can tell, used for scientific observations. Now, on the other hand, there are reflecting telescopes, which use mirrors instead of lenses. So UVA's Fan Mountain Observatory at the southern part of Albemarle County is a nice example of a reflecting telescope. And as we will soon discuss, the biggest telescopes in the world are all reflecting telescopes. They use mirrors, curved mirrors, to focus the light reflected back through a focal point and then form an image where an eyepiece might be, or where another mirror might be, to then collimate that light through an eyepiece. In all cases, though, you actually do need to have some sort of secondary mirror, whether the mirror ends up reflecting the light back out the side of the telescope or back through into an actual eyepiece and then the eye. Now, I should mention that a common question that I often get here is, wouldn't the secondary mirror end up causing a hole to be in the image, since there's this entire area that is blocking the incoming light? Well, here's the thing. The image is not created by like the sum of every little part that comes into here creating a different part of the image. No, each ray here is an entire image. So here's an entire image coming here, reflecting off over here. Here's another entire image over here, reflecting off coming here. Here's another entire image coming in here and reflecting off over here. And all of these individual images that end up getting gathered by and combined by the primary mirror and reflected by the secondary mirror, these are what end up going into creating a bright, sharp, crisp image, as opposed to just a dim, poorly resolved image. So the only thing that the secondary mirror does in terms of its blocking is it makes it so that not as many rays end up coming in, so your image ends up being a little bit dimmer than what you would otherwise expect. So as I mentioned, sometimes these mirrors end up reflecting the light off into the side by reflecting it at a 45-degree angle, and then you have your eyepiece or your CCD, that is charge coupled device, computerized method of collecting the light in here. So you could also combine multiple primary mirrors together. So the primary mirror is always at the back of the telescope. Notice that this is in contrast to a refracting telescope. In a refracting telescope, the primary lens, the main lens, is at the point where the light first starts to enter the instrument. Whereas in a reflecting telescope, the primary mirror is in the back, and then it reflects the light up to either a detector or something else that will end up focusing the light, in this case combining the light. This is an example of the Large Binocular Telescope, the LBT. So, very nice observing instrument. Now, back to refracting telescopes. Refracting telescopes have one problem. Well, they have many problems, but they have one main problem in terms of their general idea, and that's something called chromatic aberration. It only happens with refracting telescopes, and it happens for the same reason that prisms and rain droplets produce rainbows. It's because when light travels through a medium, different colors of light travel at different speeds through the medium, and because of that, they refract at different angles. That's why we get these nice rainbow patterns with thunderstorms and stuff like that. But guess what? Astronomers don't like their images to be filled with rainbows. In other words, if we have just a normal refracting lens, the blue light ends up refracting at a sharper angle than the red light, so therefore the blue light comes to a focus at a different point. So that will end up causing distortion in the colors of your image, unless it is corrected. Now, it can be corrected through a combination of things. One, you use an achromatic lens, which has a different focal length and different combined with, basically that's because you have a different radius of curvature and or different material going in here, and you also have possibly a gap between your main lens and your achromatic lens. And also you can somewhat reduce this chromatic aberration by having a very long focal length. That's another reason why our refracting telescopes are kind of these long tube-like instruments. So just kind of reminding, yep, this is what happens when you're dealing with it through a lens, but if it's different colors, they're going to be coming to a focal point and therefore forming images at different spots. Now, you can also come up with a nice little formula for the magnification of an instrument, and that's equal to the telescope's focal length divided by the eyepiece's focal length. So that's another reason why particularly refracting telescopes have these nice very long tubes to give you a nice long focal length, because the longer the focal length, the larger the magnification is going to be. So there's your nice long tube-like McCormick refractor. Now, there's something else to keep in mind, light gathering power. The larger the instrument, the more light it's going to gather. That's one of the reasons why we are building bigger and more powerful telescopes. The light gathering power is proportional to the area of the primary lens or the primary mirror. So the area of a circle is pi r squared, so if you want that in terms of diameter, plug in r equals d over 2. The point here is the area is proportional to the diameter squared, therefore the light gathering power is going to be proportional to the diameter squared. So comparing the 5-meter, that is 200-inch telescope on Mount Palomar, with one of the 10-meter Keck telescopes on Mauna Kea, well, that's a ratio of diameters that's a factor of 2. So here's a picture of the 5-meter telescope at Mount Palomar at its dedication ceremony. Even in this instrument, the smaller of the two that we're comparing, look how small the people look in comparison with the telescope itself. The primary mirror is kind of back over here at the bottom, and then it focuses the light up into here, reflecting it back. There's your secondary mirror, and then comes back. Meanwhile, the Keck telescopes are actually each much larger, and we're just looking at one of them. So a ratio of diameters of 2 means a ratio of areas of 4, which means a ratio of light gathering power of a factor of 4. So each Keck telescope collects 4 times as much light as does the Palomar telescope. And you also have 2 of them. And the Keck telescopes are also a lot more technologically advanced. We use adaptive optics very effectively with Keck. We'll talk about adaptive optics in the next video. But still quite remarkable. You build a somewhat bigger mirror and you get much greater light gathering power. Now, I should mention something though. One of the advantages of a refracting telescope is that, generally speaking, in spite of the chromatic aberration, the image quality of a refracting telescope is generally better than that of a reflecting telescope of the same size. In other words, if you look through a refracting telescope, say the 26-inch McCormick refractor, the image is generally just going to look better through that than it would look through a 26-inch reflecting telescope. In fact, this is something that I've personally experienced quite well. I've looked at the same object through the 26-inch McCormick refractor, and then on a different day used the 31-inch reflecting telescope that's one of the other tools that's at the Fan Mountain Observatory. And it just looks much better through the slightly smaller but refracting McCormick refractor. Although I would say that the 40-something inch Fan Mountain reflector, which is their main instrument, made the same thing look actually better than either of them. But still, same size, your refracting telescope is probably going to be a little bit better. So why are all the large telescopes in the world reflecting telescopes? So there's a big problem with refracting telescopes in addition to the fact that you're dealing with chromatic aberration. One of these is that when you have a very large lens, the lens will tend to get deformed by its own weight, especially as you change angles and stuff like that. After all, this is a large piece of glass that is held at the edges. Now, you can overcome that with mirrors because mirrors are supported underneath. So what you can do is you can use something called active optics. As the angle of your telescope changes, you can have a computer gradually apply more pressure to different parts of the back of that mirror to help it maintain its shape so that it doesn't end up deforming due to its own weight, or at least so that, make it maintain its shape so that the image doesn't end up getting affected. So you can do this with reflecting telescopes because, you can just apply pressure in the back of the mirror. But you can't use pressure pads applied to the back of a lens because the lens needs the light to pass through the lens. It's not getting reflected back. It's not getting refracted back. So the light needs to pass through. So the only way you can support a lens is by holding the edges. So as a result, you can make your reflecting telescopes, the ones with mirrors, much bigger. Another problem is that as you make your lens bigger with refracting telescopes, remember where the lens is. The lens is at the opposite side of the tube from where the observer or the CCD is. So since it's on the opposite side, that's a very heavy object, very heavy piece of glass there. It's going to cause large torques, making these types of telescopes difficult to control if you have a very large lens. As a result, the largest refracting telescope in the world is the Yerkes refractor. It's in Wisconsin, but it's controlled by the University of Chicago. The tube is 64 feet long, and the lens is about 1 meter wide, so it's like 40 inches wide. But this is the largest and biggest, longest, widest aperture refracting telescope in the world, just 40 inches. Remember, we were just doing a comparison problem with a 5 meter compared with a 10 meter reflecting telescope. So Yerkes Observatory is quite nice, but again, you can only, it's the largest possible refracting telescope, or I shouldn't say the largest possible, but the largest one that's ever been built. And even in that case, they were getting kind of close to the limitation of what you could really do and have such an instrument perform effective astronomy. So even though the image quality isn't as high with reflecting telescopes, you can make them to be much, much bigger. And because, again, they're supported by their backs. Also, remember, mirrors don't suffer from chromatic aberration. In other words, angle of incidence equals angle of reflection regardless of the color. So all of the colors reflect at the same angle. And also, in addition to that, we already discussed active optics that can help you to adjust the shape of the mirror with pressure pads in the back of the mirror. Well, there's also something called adaptive optics that we'll talk about in the next video that is a very powerful technique for compensating for atmospheric turbulence. So this is something that we will get into in more detail in the next video. So returning to our question, why are we building bigger and more powerful telescopes? We've already addressed one of the reasons. That is because with a larger telescope, you can collect considerably more light, therefore significantly decreasing the necessary observation time, or being able to look a lot deeper into the universe using the same observation time. But there are other reasons as well. First, starting off with resolving power. And this is what we will begin our next video with. So hopefully I'll see you then, and thank you for watching.